Okay, we're doing a resistor test on this instead of using the meters. First thing I want to clear up is this situation here with our power supply. This is nothing more than an AC transformer that puts out a square wave instead of a sine wave. We will be measuring the current this system is using in between the output of our transformer and the input of our circuit across that 1 ohm resistor. As far as the transformer itself goes, I'm not interested in how efficient that is. I'm interested in what this circuit here is using and what it is putting out. I have the coil hooked up to an alligator clip lead simply so I can connect it and disconnect it and show you what's happening. So of course that is the wave there on the input side across that 1 ohm resistor. I am set on the 50 millivolt divisions for our volt divisions and 2 microseconds on our time divisions. I have moved the trace across so the pulses change from high to low side at the center line of the scope, and this will become apparent a little later on as to why. So that's our wave from our across our 1 ohm resistor without the coil hooked up, and I will hook the coil up and you will see that the wave squares up nicely with the coil hooked up and we get a little bit of a spike at the start. That's disconnected, that's connected, very little change. The voltage drops off a little towards the end of the pulse when it is disconnected, and when it is connected it stays nice and square. Okay, so we'll leave the coil disconnected and we will put the scope across each of our 1 ohm output resistors. Once again we are about, well, we're dead on 2 divisions on the low side, which will give us 100 millivolts, and on the high side we are about 90 to 95 millivolts. Both of course drop off towards the end of the pulse with the coil disconnected. So while it's disconnected we will check our output resistors. That is 1, so that is 1/2, that's the low side of the pulse you're seeing, which is identical to what was going in. Drops off slightly towards the end of the pulse. I will now swap it over, and I'm keeping it polarity correct on the input and the output, which makes it a bit easier. As you can see, these two here are in fact going to the common, which is where I'll keep the probe, that is the input, and this is going to our load. So now I don't know what's happened here, but I'm not getting any pulses across that side. Try the level a bit. No, there we go. Okay, that is the high side, and as you can see it's exactly the same as our input resistor, which it should be. So the current across the input and 2 output resistors are identical. So I'm going to put the scope back on our input resistor, and I am now going to hook up our coil. So you can see that it's squared, the pulse is up nicely. We do have a little bit of a spike at the start, nothing real fantastic at all. Okay, so we're now going to check the output across the resistors with the coil hooked up. So now you can see a clear difference. We are down to about 125 millivolts across the resistor, and it tapers up to about 110 millivolts. Now this is the low side pulse, which is on the left side of our centre line. Okay, and I just want you to remember that, because it's what you will see when I swap over to the other output resistor. You can now see that we have the same as we did on our input resistor on the pulse, but it drops down and then the voltage maintains itself. It does not drop to 0 volts across that pulse, and this is of course our low side pulse. So the potential voltage across that resistor now has increased quite a bit compared to our input. To show you this, what I can do is I will disconnect. As you can see, that was the same as our input, and now I'll connect the coil, and you can see the difference it makes. So it's disconnected, connected, and I will swap it back over to the low side. Not that earth is a bit, the ground is a bit loose. There we go. Okay, that's disconnected. That's connected. Disconnected, which is the same as our input pulse, and that's with the coil connected. So you can see the voltage increase across that output resistor, and as I showed before, put our scope back on the input resistor. That is the coil disconnected, connected, connected, disconnected. So the change on the output, across the output resistors, is far greater than the change in voltage across the input resistor when we add the coil. Now keeping in mind, I should have ran through this circuit a little more than what I did at the start, but we have eliminated the 2 input diodes which are there. They are the 2 outputs for our diodes, and we have gone straight from the resistor, goes straight into the input after the diodes and around to our centre pin here. So there's no diodes to take into account anymore. They can't be dissipating any of the current or anything like that. We're going straight to the input. So one of 2 things: either Ohm's law doesn't apply exactly as it states. Well, that's a nice big dragonfly. Or we have a circuit that warrants a little more looking into. So that's what I have to show, using 1 ohm resistors on the input and the output. They are 1 watt, we're using far less than 1 watt. There will be no heat loss at all. Also keep in mind that the coil is in parallel with ground and the output not in series. So that would actually lower the resistance even further on the output rather than making it higher. Okay, that's it from me. Cheers from the Tin Man.